Hello, everyone. My name is Vladimir. I'm going to present our work titled Building Implicit Vector Representations of Individual Coding Style, which is a collaboration between my colleagues and myself at JetBrains Research in St. Petersburg and Amsterdam, and Alberto Bacchelli at University of Zurich. Let me start from afar. We don't really have time to go too deep into detail anyway, so I'm going to use a good chunk of the 10 minutes that we have to share and motivate one important message. And my goal with this talk is not really to tell you many details about this piece of work, but rather to convey this message and spark up a discussion. The message is we need better models of collaboration to empower smarter team collaboration tools. Let me explain. We're familiar with IDEs, and IDEs offer plenty of options for code manipulation and analysis. One can refactor code or find and fix multiple issues with just one click. And what enables IDEs to be so smart and do these incredible things with code are rich internal models of code and various connections between its elements. For example, the IntelliJ platform and its IDEs like PyCharm, WebStorm, or IDEA all rely on so-called PSI, which is a program structure interface. It is a tree-like representation of the whole project, from directory structure down to elements and code, that powers most of the refactor and analysis features. Well, software engineering is not just about code. I'm happy I don't have to sell this idea to this audience. Software engineers use tools to collaborate, manage tasks, and socialize, as well as to write and manipulate code. And one thing that makes collaboration tools different from IDEs is a relative simplicity. So most of collaboration tools and their features essentially just provide a way to manipulate and display rather simple data, like text or issue fields in issue trackers, or code in code review tools, which is pretty much represented as text as well, except for highlighting. And they don't build or use any models of the processes they support, which is communication and collaboration. And as a result, they don't provide any smart features to users, with a few exceptions, of course. So there are things like recommendation systems based on historical data, but they're not too widespread just yet. So to sum things up, IDEs are about code, and they have great code models which help them to be powerful tools for working with code. And team collaboration tools are about communication and collaboration, but they don't have any models of these processes. And here comes my message again. To make team collaboration tools smarter, we need to empower them with rich models of interpersonal communication and collaboration in teams. And when I say smarter, I don't just mean more automated. I also mean better tailored to users' needs. So this picture is from a rather famous paper on expectations and outcomes of modern code review by Alberto Bacchelli and Chris Bird. This picture presents the most frequent motivations reported by developers for doing code review. The cool thing is, most of these motivations are not really about code, but rather about sharing knowledge with each other. But the code review tools that we have today are far from offering substantial dedicated support for knowledge sharing. And one reason why they don't have those features for knowledge sharing is they just don't have any models of knowledge and knowledge sharing in teams. And this brings me to our work, which is a step in this direction. The goal of this work was to try and build representations of individual coding style of people. This is a really important element of the collaboration models I've talked about earlier. So if we had such representations, or if tools had them, it would be possible for them to trace evolution of individual coding style and even detect learning between people. This would bring the tools closer to offering assistance or steering this process where necessary. Think of phenomena like buzz factor. So tools of the future may actually be able to assist with maintaining a healthy knowledge distribution in the team. So for this work, we define coding style as vaguely as whatever makes one's code different from peers' code. This way, we're not limited to any particular set of metrics, like, for example, some work on code stylometry that's been published. And it's good not to be limited because every set of metrics is naturally limited. It cannot just capture every aspect. So we may miss some important elements if we use a predefined set of metrics. Here is an overview of our pipeline. First of all, we train a machine learning model to attribute authorship of code changes. Essentially, what the model learns under the hood is to vectorize individual code changes in such a way that changes that are authored by different developers are separated between each other as well as possible. When we have this representations of changes, we aggregate multiple changes from many people or the representations into one vector that represents the developer that made the changes. So essentially, a person is a sum of code they change or changes in the code they make. So the output of the model is multiple snapshots of coding styles from multiple developers in the team, with each snapshot corresponding to a particular time period. So our hope is we could maybe make sense of these representations, like from the relative positions and the relative movements. For instance, relative positions of representations could hopefully represent proximity of individual coding styles, and speed of the relative movement could represent learning. I wouldn't go too deep into details on how the authorship attribution model works. I will only say that it's a modified version of code2vec. You can read more in the paper. The interesting part here is relative positions and relative movements of representations. We hope to be able to make sense of it, but can we really? So if A and B are close or are moving closer to each other, does that mean that there is a learning between them? We tried to check it with a survey. First, we computed the representations of coding style from contribution history of a really large project, which was in the IDEA community, and asked the developers to indicate peers from whom they've learned some elements of coding, and also separately indicate some people in their team they're sure they didn't learn from at all. After the survey, we had 23 pairs of people where one person reported learning from the other, and 13 pairs where one person reported not learning from the other. For every pair, we calculated distances between representations of those people in 20 different time buckets, and also looked at changes in the distances over time. Finally, we compared distributions of these distances and their differences, so relative speeds of representations as they move. What we found is distances between people, one of whom reported learning from the other, are actually lower, significantly lower than in pairs where one reported not learning from the other. But there was no effect we could observe for distributions of differences of distances. From this, we conclude that our code style representations may capture learning, and actually do capture learning between individual developers to an extent. To sum things up, we need rich models of collaboration to improve team tools, which are not too smart yet. In this work, we build representations of individual style just from technical records. It's important. It's fully automated and unsupervised, so you can just run it and get representations. And these representations, to an extent, capture learning between developers. This is a really exciting direction of research because the team tools of the future will one day evolve to offer supporting collaborative processes, and we made a really good step towards this. There are a few issues. I'll mention them really briefly. Data is noisy because of the randomness of the machine learning model, so we had to run it multiple times and then average. It's slow. Our evaluation was just for one project, which is not as good as it could be. And finally, the authorship attribution model distinguishes between people not just based on style, but also on context. You can read more about this in the paper, and thank you for your time.